discuss the set theory. That's really important for probability theory because the base of probability theory is the set theory. This is how we define probability because probability is defined in terms of sets. So probability the function that maps events to a real number. So events are the sets. So hence set theory is the base of the probability theory. So let us talk about set theory that is related to probability theory. We are not going to discuss sets, types, and etc. We will be only talking about um, set theory that's only related to the probability theory. So let us talk about it. Um, we start from the sample space. The definition of the sample space is that the set of all possible outcomes of a particular experiment. So here two terms are used: outcome of a particular experiment. So another term is particular experiment. So if I give you an example here, if you see, if we toss a coin, so tossing a coin is an experiment, and in the result of tossing a coin, a fair coin, we get either head or tail. So these head and tail are the outcomes, and tossing a coin is an experiment. So what you are actually doing is an experiment, and what you get in the result is called the outcome. So if you are getting some outcome in the result of some experiment, if you collect all of the outcomes, all of the possible outcomes that can be possible, we call such a set as a sample space. So this is one of the examples. So first example. Another example is a SAT scores that are reported. We know that the SAT scores are reported as a multiples of 10 and they are between 200 and 800. So if someone scores, they can score 200, 210, 220 up to 800, and there is no other numbers. So it's only multiple of 10 and between 200 and 800. So this is also simple space for SAT score. Now let us talk about the time that is measured exactly, the reaction time that is measured exactly. Exactly, when we are saying exactly time, it can be any number between 0 to infinity, right? So it's like it can be like square root 2, it can be 1.333. So we don't know. We cannot say it's 1, 2, 3, 4, 5, and so on. It can be any number because we are saying exactly word. So the sample space would be 0 to infinity, and 0 cannot be included because the reaction time cannot be 0, um, because we are saying exactly. And if waiting time is measured to the nearest second, now for example, if I have 0 0.1, the nearest integer is 0. If I talk about 1.5, 1.6, say suppose, the nearest integer is 2. So in such a way, like all of the nearest seconds um, are 0, 1, 2, 3, and so on, which are positive integers, and 0. Now we talk about two um, kinds of simple spaces. One is countable and another is uncountable. So what's the countable set? Countable simple space. We say a simple space is a countable if its elements can be put into one correspondence with a subset of integers. So this is really a good definition because it covers finite sets as well and infinite sets as well. So if you have like, now what do we mean by one correspondence? For example, if I take this example, 0, 1, 2, 3, and so on, I can associate 0 with 1, and I can associate 1 with 2, and so on, and so on. So this is like there is a one correspondence between this set of natural numbers and this 0, 1, 2, 3, and so on. In fact, 0, 1, 2, 3 is a subset of positive integers. Is subset of integers. So this is itself countable by definition. And for example, if we take some finite set, let us take 200 to 800, the multiples of 10. This is um, corresponding to, this is also a subset of positive integers. You can correspond it to itself, or you can correspond it to 1, and this to 2, and up to so on. So this is also 1, 2, 3 up to so on is also subset of integers. So that's the countable set. So countable space can be either finite or it can be infinite. Okay. So let us talk about now a sample space that is not countable. So the example is 0 to infinity, the reaction time that is measured exactly. So the sample space is 0 to infinity is uncountable because you cannot give correspondence to every number like 0. If you take 0.1, then you are missing some number between 0 and 0.1 and so on. So this number cannot be, this set cannot be countable. This is uncountable. And while this set 0, 1, 2, 3 and so on, this is infinite, but it's also countable because it's a subset of integers. So this is a countable infinite set. Now let us talk about um, the definition of event. What's event? Since we know the sample space and the outcomes, so the definition of event is that any collection of possible outcomes of an experiment. In other words, an event is any set of S, subset of S, including S itself, because S could be set of itself. So a set is an event if and only if A is subset of S. So any subset of S, any collection of outcomes is called event. So we have used here the this word subset. We will be defining like what do we mean by the subset. Um, so here we talk about what is subset. So A subset of B if and only if every element of A is an element of B. All right. Let me choose another pen. So if every element of the A is an element of B, then we call it subset. If we talk about if we take an example, one set is this 1 2, in the set is 1 2 3, let's say 4. Every element of this 1 is here, 2 is here. Every element of the set first set is an element of the second set. We call it a subset. All right. So here we missed a definition. It's not a definition. It's a like term. What do we mean by event has occurred? If some outcome of the experiment belongs to A, set A, we will say the event has occurred. For example, if I take an event A, which is like 1 2, if experiment, if 2 occurs, if we are taking possible outcome 2, okay, so this 2 belongs to A, then we will say this event A has occurred. Even 1, we are not taking 1, okay, so because this is 1 or 2. So if 2 has been introduced, 2 has come out, then you can say event A has occurred. If some element of the set has um, belongs to set A, then we say that that event has occurred. All right. So it's a definition of you can say like this is how we define the term like the, the event has occurred. What do we mean by event has occurred? If an element of the set A has occurred, just one element at least. Okay. Now we talk about subset. So the equality of the sets. So two sets are equal if and only if one is contained in another and another is contained in the first one. So if they are like contained in each other, then we call it two sets are equal. And now we define two operations: A union B, which is X belongs to A or X belongs to B. A intersection B is X belongs to A and X belongs to B, which is contained in both A intersection B. A complement is the set such that X is not in A. So now let us take an example. Um, Consider selecting a card from a standard deck and recording its suit. So suit can be like club, diamond, hearts, or spades. So these are C, D, H, S. And if we take an event C, D, so if we talk about now C, if C has occurred, then we will say event A has occurred. If D has occurred, event D has occurred. It's the meaning of like what do we mean by set has occurred. So this is set A and set B is DHS. And if we union them all, we get CDHS. And if we intersect them, we see that D is the only intersecting point which is common in both, which is the intersection B. And A complement means what? The elements that is not in A. So what's not in A? We see that H and S are the two elements that are not in A. These make set A to be simple space. If we give set A to its complement, then set A would be a simple space. So this is a complement of A. This is what set A needs to be a simple space. So if we see A union B in terms of this thing, like what needs A to be a simple space, what needs A union B, which is a S. A union B is what? S. What need simple space to be a simple space? It needs nothing. So A union B complement, S complement is actually nothing. It's an empty set. Now we talk about some elementary properties. So first property we call the commutative property with respect to union. That if you union A with B or B with A, the answer would be the same. If you intersect A with B or B with A, the answer would be the same. This is commutative property with respect to union with respect to intersection. And this is called associative property with respect to union, associative property with respect to intersection. This is intersection over union, and this is union over intersection. These are two distributive properties. And like these two um, identities, we call them De Morgan's law. So we will be proving only one property, which is distributive law, intersection over union. So how do we prove two sets are equal? We need to show that this one is subset of this and this one is subset of this. So let us take an element from the left hand side and we need to show that it's in the right hand side. If X is in A intersection B union C, then by definition X is in A and X is in B union C. So if X is in already in A, so you need to remember that X is in A now and X is B union C. If X is in B union C, then X could be in B or it could be in C. So since X is in A is fixed, if you combine this statement with X is in A, this becomes X belongs to A intersection B. If you combine this statement with X belongs to A, then X belongs to A intersection C because X is already in A. So if X is in C, second case, then X would be in A intersection C. So in both cases, X belongs to either A intersection B or X belongs to A intersection C. This OR is inclusive OR. So it's not like just either or, it's like just or. It could be in both. Now we talk about the converse. X belongs to A intersection B, union X belongs to A intersection C. So by definition, X belongs to A intersection B or X belongs to A intersection C. In either case, we note that X is in A. So X is in A in either case. And we have either now X belongs to B or X belongs to C. So because X is in A is fixed. So now whether X would be in B or it could be in C. So hence X belongs to B union C. Hence X belongs to A intersection B union C. So therefore we have this containment is true. So we proved the containment like both sided. So hence this is A intersection B union C is A intersection B union A intersection C, which is a distributive property intersection over union. Now, if we have infinite sets, a sequence of sets, how do we define union? It's the same thing. Take those elements from S such that X belongs to AI for some I. For some I means I could be anything. I could be 1, 2, 3, 4, and so on. So that means you are collecting all of the elements that are in AIs. So this is like combining all of the elements from AIs. Intersection AIs means all elements in AIs are all elements in S such that X belongs to AI for each I. That means X is in A1, X is in A2, X is in A3, and so on. So intersection of AIs. If we take an example, take sample space to be 0 to 1, and this is an event because it's subset of F's. Clearly, if you take 1, 2, 3, and so on. So if you union all of them, so if you see on the number line, this is 0, this is 1, this is 1 half, this is 1/3, and so on. So if you take first A1 is 1 over 1 comma 1, which is just 1, and A2 is like this one, 1 half to 1, and this is 1/3 to 1, and so on. So if you see that we are getting very close to 0, but we cannot get 0, right? So that means 0 will not be included. So this would be like 0 to 1. So union of AIs is 0 to 1. If you take intersection of AIs, so the smallest set is this one, 1, because if you take A1 1 to be 1, so then you get this one. So an example of infinite sequence of union and intersection. More generally, you can take any set gamma, not necessarily to be integers or positive integers. It could be any uncountable set. This is how you define the same way, and this is how you define the intersection in the same way. So this is an example. If you take gamma to be 0 to infinity, A alpha is 0 to alpha, then union of alpha is 0 to infinity. Now we talk about disjoint sets. What is a disjoint set? Two sets A and B are said to be disjoint or mutually exclusive if there is nothing in common in between. Their intersection is empty. And if we take a sequence, we call a sequence a pairwise disjoint if any of the two elements, a different two elements, I is not J, if you take any two elements, they are disjoint. So that's why we call it a pairwise disjoint. If you take any pair, then that's a disjoint. We call it a pairwise disjoint sequence. So here's an example. It's a pairwise disjoint sequence. If you union all of them, then you get a sample space 0 to infinity. Now you define partition. What's a partition? Partition is again a sequence that is a pairwise disjoint. And if you union all of them, here 0 to infinity is not necessarily to be sample space. I just said, which is not true. 0 to infinity could be a sample space. It could be a subset of sample space. So if the union of such AIs, which are pairwise disjoint, if you get them to be a sample space S, then we say this sequence form a partition of S. So if you take this space to be a simple space, then this sequence of events, these are pairwise disjoint for sure if you see on the number line. And if you union all of them, you get 0 to infinity. So this forms a partition for 0 to infinity. So this was the basic set theory that was necessary for the set theory, for the probability theory.